For the fundamental theorem of calculus, part 1, we start with considering a continuous function f. We want it to be continuous on a closed interval, a to b. So my function could perhaps look something like this, where here's a and here's b, and it's continuous on there. Then when we define the function g of x, which is going to be the integral from a to x of f of t dt, where x is going to be between a and b, where we're guaranteed continuity of f. Now, it makes sense to talk about the integral. It makes sense to talk about the area under the curve because it's nice and continuous, which we can see in that picture. So from a to x, g of x outputs this area right here. So we can move x between a and b, and we get different values for the area under the curve. So this g of x is our area function. And the result of the fundamental theorem, if we define this particular g of x, we get that g is continuous on that a to b as well. And moreover, g is differentiable on the open a to b. And even better than knowing that it is continuous and it is differentiable, we actually know what its derivative is. So it's differentiable on a to b with g prime of x being exactly f of x, which is that original function. So the result of the fundamental theorem of calculus tells us that if we start with an area function, where we're computing the area under a specific curve, f of t, then the derivative of the area function just exactly gives us the curve back. So the derivative of the area function is the original function. For example, if we look at the area function g of x, which is defined to be the integral from 1 to x of t squared minus sine of t, so that's our f of t dt, we can find its derivative. We know that t squared minus sine of t is a continuous function on all real numbers because t squared is a polynomial and sine of t is continuous on negative infinity to infinity. So it will be continuous from 1 to x. So we can apply the fundamental theorem of calculus, part 1, to obtain that g prime of x will be f of x. So everywhere we see a t in f of t, we replace it with an x, and our g prime of x will be x squared minus sine x. For the fundamental theorem of calculus part 2, again we start with considering a continuous function f, something like the picture down here, and it's continuous on that closed interval from a to b, and we want to consider computing the definite integral from a to b of f of x dx. So that's this area right here. And because of this amazing relationship that we have between the area function and the derivative, it turns out that this calculation is exactly capital F of b minus capital F of a, where capital F is any antiderivative of little f. Okay. i.e., if I take the derivative of capital F, I get little f. In this example of applying the fundamental theorem of calculus part 2, we're going to compute the integral from 1 to 2 of x squared. Now x squared is a parabola, so it's continuous on negative infinity to infinity, and it's continuous from 1 to 2. So I can compute this integral by using the fundamental theorem of calculus part 2. So for f of x being x squared, my capital F will be any antiderivative of x squared. So I add 1 to the power, and I divide by the new power, and I obtain 1/3 x cubed. And that'll be my capital F of x. Now, in general, we know for the most general antiderivative, we need to add a plus c. But if I think back to what the Fundamental Theorem Calculus Part 2 said, it said I can use any antiderivative. So we'll use the antiderivative where plus c is 0. So it looks like that. So we need to compute capital F of b, which is 2. So that'll be 1/3 times 2 cubed, or 8/3. We also need capital F of 1, which will be 1/3 times 1 cubed, or 1/3. So when we go back now to working out our integral, this will be capital F of 2, which is 8/3, minus capital F of 1, which is 1/3. So the definite integral from 1 to 2 of x squared dx is equal to 7/3.